everybody, this is a lesson on substitution with definite integrals. So just to be clear what we're going to be looking at, problems like this, where you use substitution, but now it's a definite integral, so you've also got, numbers here or whatever. So if you've never watched my videos before, I highly recommend you pause and try the examples when prompted, and there are always free guided notes available at divideandconquermath.com. So to warm up, I'm assuming that you already understand how indefinite integrals work, so there are no numbers here. So I'm actually going to be using these examples throughout the video, so I thought this would actually be a great warm-up just to make sure that you kind of know what's going on. If you're struggling with these, I would highly recommend just going back and mastering doing substitution with indefinite integrals, because basically then I'm assuming that you've already gotten good at this, and I'm going to add on another step. That's basically what makes this what it is. So pause the video here, do these two just to get warmed up, and then we can get started. Okay, so just to go ahead and evaluate this one. So in this case, my u is going to be 1 minus x cubed, and my du will be negative 3x squared dx. And so now I can see just by looking at this that this doesn't totally work. There's a couple different ways you can kind of do your substitution, so I kind of mix it up in my videos. So what I'll do in this case is I'll just solve this particular expression for dx. So if I solve this for dx, I get du over negative 3x squared. So now I'm going to make these substitutions. So I will now have nothing to substitute quite yet for 6x squared. We'll deal with that in a second. But in this square root, this will be where my u is from. So I'll just rewrite this as u. Then I'll replace my dx with this part over here. So this will be du over negative 3x squared. Okay, so now what I can see that I'm left with, so the x squareds definitely drop out, and then negative 3 will go into 6 negative 2 times, right? So or negative 3 divides into 6 negative 2 times. So I'll cross this out, I'll cross this out. This will actually become negative 2 on top. So maybe this is a little bit difficult to see, so if I just now write this all out, so what I'm actually left with is negative 2, actually I'm going to rewrite this as negative 2u to the negative 1/2 du. So I just like writing it out in its exponential form when I'm integrating. So then I can finish this. So this will be negative 2 times 2u to the 1/2 plus c. So this will be negative 4, 1 minus x cubed to the 1/2 plus c. So we'll leave it like that for now. So like I said, ideally where you should be, this problem should be pretty straightforward actually. This should not be a problem at all. If you're just totally struggling with this, then I think it might be best just to go back and make sure you've mastered this before we added on more stuff, Okay, so now for this other one, this one's a little bit more challenging. So for this one, my u is 1 plus x, and then my du is going to be 1 dx. So you'll notice when you kind of substitute this out that, so my du will just directly replace this dx. Here's where I will substitute my u, but I didn't have anything that would kind of replace this x. So the thing I just want to note here then is if u equals 1 plus x, then what this means, and maybe I'll just make my x look a little more clear. Here, let me erase that. So my u is 1 plus x. Therefore, if I solve for x, my x is equal to u minus 1. So this is a really standard trick that we use for substitution. So then I can start substituting. So the top of this will become, let's see, u minus 1. The bottom will be u to the 1/2. So I just rewrote it in square root form. And then my dx I can just replace directly with my du. So now that I have this written out, I can actually see that I could break up this fraction. So this is like a totally different problem now. So this will be u to the 1/2 minus u to the negative 1/2 du. So I'd rather integrate this because then I can just think through the exponents and work through the power rule and all that. So now if I go ahead and evaluate this, this will be 2/3 u to the 3/2 minus 2u to the 1/2 plus c. And then if I replace everything, this will be 2/3 times 1 plus x to the 3/2 minus 2 times 1 plus x to the 1/2 plus c. So again, I'm kind of assuming that you've already mastered this, so I've kind of plowed through this example. So if you really need the breakdown, just one more suggestion of going back and watching some of the other videos I have. Okay, so now let's get into what this lesson's really about, which is now I'm going to basically take these examples and turn them into definite integrals. So I'm just going to put like numbers here. So there's two different ways that you can do this. So we've actually done like all the heavy lifting so that we can just focus on what do you do with this. So there's two different ways that you can kind of deal with this. So in way one, you basically evaluate the indefinite integral version of this. So what I mean is you would literally go through this problem, which we just did, right? So that's why I made you do all that. So you would evaluate this. We already know what the solution is to this, right? So we already said that this was -4 times 1 minus x cubed, let's see, all of that to the 1/2 plus c. So we already did all this. So you'd find this answer, and then basically you would just plug in your limits of integration. So then I would take, so I can just drop out off the plus c. So it would look like this. So I've got this, and then I'm going to evaluate this from 1 to 3. So that's basically one way that you can do this. And then you just plug everything in like you normally would. So this would be 1 minus 3, let's see, oops, this is x cubed, and then this would be 1 minus 3 cubed to the 1/2 minus -4 times 1 minus 1 cubed to the 1/2. Okay. Okay, so now if I go through and I evaluate this, so this really leaves me with -4 times the square root of -26, and then this whole thing will just be -0, right? Because 1 minus 1 is 0, so this whole thing is just 0. So I'm just going to leave it like this. I know I could simplify this farther, you know, write this as an imaginary number. It's not, for the point I'm trying to make, this is fine for what we're doing. So just remember this answer here. So this is the first way that you can do this. So now I want to show you another way to do the same problem. So the second way is you change the limits of integration. So I make all of my substitutions. So I'm just going to remind you, let me just quickly write down what we had before. Okay, so there was my u and my du. Oops, and I forgot the dx. So you start going with all this, and then basically what you do is you also work on the limits of integration. So I'll color code this just so you can really follow my reasoning. So starting here with 1. So I'd say if x equals 1, then u equals, and what you're going to do is you're going to reference this formula here. So whatever you set your u equal to, this is how you're going to change your limits of integration. So this becomes 1 minus 1 cubed. Notice I just plugged the 1 in for the x, so this would be 0. Then for this one, I have if x equals 3, u equals 1 minus 3 cubed, so this will be -26. So now when I change the problem up and I'm putting in all my u's, I'm actually going to also change my limits of integration. So I'll keep this color coding up just so you can follow it. Okay, so where I had this 3, now I'm going to replace it with -26. So this now becomes -26. Then this 1 now becomes a 0. And then all of these other substitutions, these are things that we already discussed, right, in the problem. So I actually rewrote this whole thing then as -2u to the -1/2 du. So all this stuff with the indefinite integral still stays the same. Now, you have a few options here. You can totally just plow ahead with this problem as it is. And I know that the limits of integration, usually it's the higher one goes on top. But you could totally just have it like this, that like there's nothing wrong with this. It just, sometimes it kind of just bothers people to have it like this though. So some people just insist on flipping the limits of integration like this. So if you are one of those people where it just has to be a certain way, that's totally fine. If not, you can plow ahead with it. You'll get the same answer. Okay, and so I've got a negative and a negative. So then this whole thing becomes a positive. So hopefully you saw that. So now I can finish the problem. So this will end up becoming 4 times u to the 1/2 plus c, and you might be saying to yourself, well, this looks, oops, sorry, and there is no plus c, my bad. So this is 4u to the 1/2, and so then I'm gonna do this, and you might be saying to yourself, well, this looks different from what I had before, but remember, we're just now looking to see if we get the same numerical answer, so hold that thought. So now if I go ahead and finish this, So the nice thing about this is that you never have to go back to the original limits of integration. Basically, you change this once, and then you just plow through the rest of the problem. So if I were to now evaluate this, this would be, let's see if I have enough room, 4 times 0 to the 1/2 minus 4 times negative 26 to the 1/2, and yep, I'll have just enough room. Negative 4 times negative 26 to the 1/2. Hey, look at that. It's the same thing as what we had before, right? So square root of negative 26 is the same thing as negative 26 to the 1/2. So 6 one way, half a dozen the other. So we got the same answer. So this is just a nice method if you just want to plow through it and you don't want to have to remember to do the limits of integration. I think this is also a really good way to go if you are prone to forgetting to actually evaluate the definite integral. I know a lot of people say, oh, I like this method because, you know, that I don't have to change anything. But what I notice happens a lot, and so you just have to figure out if you're one of those people. Some people will plow through this and they get to this step here, and then they totally forget about the definite integral, so that they had to evaluate anything. So that can always be a little bit of a devastating blow. So if you are prone to that, then you definitely probably want to use way 2 so that you just don't forget. So this, I know, always feels a little bit awkward at first when you're trying it. But once you get used to the idea, I think it's a little bit faster. But then again, I'm a math teacher. So, okay. Now what I want to do, I want to use the other example that we started with, and I want to give you a chance to try both ways. So now what I want you to do is first just try this using way 1. So you should already have the answer to the indefinite integral, so you can just finish this. So go ahead and pause the video, hit play when you're ready to just check your solution. Okay, so where I want to start is I just want to evaluate this indefinite integral, and I'm going to omit the work here because we already did all of this at the beginning. So I already know that this is the answer, so I'm just going to write that down one more time for reference. So you find this part, and then you can discard the C, and you're basically going to plug in now your limits of integration into what's left over. So what I'm looking at then is this is going to be 2/3 times 1 plus x to the 3/2 minus 2 times 1 plus x to the 1/2, and I need to evaluate this from 0 to 3. And so if I plug everything in, so let's see, this will become 2/3 times, so let's see, 1 plus 3 to the 3/2 minus 2 times 1 plus 3 to the 1/2 minus 2/3 times 1 plus 0 to the 3/2 minus 2 times 1 plus 0 to the 1/2. Okay, so you're going to plug all of this in, and I'm kind of running out of room here, so I'll write down what the final answer is. So the final decimal that you should have gotten when you plugged all of this in. So first of all, you will get a fraction and a whole number. So if you're computing this by hand, you'll get to 14/3 minus 2. And then if you're going for like a full decimal, this will ultimately equal 2.67, or you get it in fractional form, whichever way you got the answer. But this is what you should have gotten to after you plugged all this in. Okay, so that's way 1. Now let's try way 2. So in this way, I want you to change the limits of integration. Again, you already know what the answer is, so you shouldn't get too bogged with that, but just have some experience doing that. Pause, hit play when you're ready. Okay, so just to remind you, so my u in this case was 1 plus x. My du was dx. Then if x equals 0, what that would mean then is that u will equal 1 plus 0, which equals 1. And then if x equals 3, then u will equal 1 plus 3, which equals 4. So then if I restate this whole thing, what I'm going to get is this now becomes, this goes from 1 to 4, so using these new limits of integration. And then the rest of this, we already covered all of this, so this is still that u to the 1/2 minus u to the negative 1/2 du. So I'll plow ahead with this now. So I get, once again, 2/3 u to the 3/2 minus 2 u to the 1/2, and then I need to plug in these numbers, and I never have to go back now to the old limits of integration, so I can just plow ahead. And so then I'll get 2/3 times 4 to the 3/2 minus 2 times 4 to the 1/2. So don't forget you're plugging 4 into both pieces here. And then you're going to subtract off plugging in 1. So this becomes 2/3 times 1 to the 3/2 minus 2 times 1 to the 1/2. So I have to evaluate all this. And I'll ultimately still get to the same thing. So my answer will still come out to that 2.67. So again, I'm just going to kind of omit that work just so you can kind of see what you have to plug in though. And you'll notice that like the numbers that you're plugging in, probably a lot of times this is going to work, right? So this comes out to 4 here. And if you look at the way that you did this in way 1, so 1 plus 3 is 4. So there is like a connection kind of in how these things are working out. So you kind of end up doing this work up here. You kind of end up doing it either up here or you do it later in the problem, as we kind of see down here, if that makes sense. So that is really what makes substitution with definite integrals just a little bit different. So it's really just all the same stuff from indefinite integrals with a little bit of a twist. So that's it for this video, but if you're looking for more examples, I do have more examples, so feel free to check those out. And I will see you guys next time. Thanks for watching.